There is a point on the map that controls the destiny of the world, a strait just 33 kilometers wide, through which 20% of all the oil consumed on the planet passes. Every single day, without exception, the Strait of Hormuz, the most strategically critical bottleneck in the global economy, handles this flow. If it closes, the world will not merely run out of oil, it will also run out of plastic, fertilizers, medicines, and electricity. Markets collapse within hours. Wars begin within days, and disrupting it is surprisingly easy. An armed conflict, a diplomatic crisis, a few floating mines at the wrong moment. Iran has threatened to close it dozens of times, and every time it does, the price of a barrel of oil rises within minutes. The countries of the Persian Gulf have lived with this threat for decades. Saudi Arabia, the United Arab Emirates, Kuwait, Iraq, trillions of dollars in oil reserves that can only reach the world through this single vulnerable point. The solution exists. It is brutal in its ambition, extraordinary in its engineering, and carries a price tag that would make any government on the planet go pale. $200 billion, an artificial canal, hundreds of kilometers of desert to be crossed, the largest infrastructure project humanity has ever attempted. That is what it would take to build the canal around the Strait of Hormuz. First, we need to understand the problem in its entirety. The Strait of Hormuz separates the Omani Peninsula to the south from Iranian territory to the north. At its narrowest point, it measures just 33 kilometers. The effective navigable channel is even narrower, with two 3-kilometer lanes and a central waterway between them. Between 17 and 21 million barrels of oil pass through those lanes every day, the equivalent of the combined daily consumption of China, India, and Japan. All carried on ships, supertankers 300 meters long, one after another, without stopping, day and night, 365 days a year. There is no alternative, no pipeline crossing the strait, no alternative shipping route. If the Strait of Hormuz closes, that oil goes nowhere. The Gulf countries already have some pipelines that partially address the problem. Saudi Arabia has the Petroline pipeline, which crosses the Arabian Peninsula from east to west and reaches the Red Sea. Its maximum capacity is 5 million barrels per day, half of what passes through Hormuz in a single day. The United Arab Emirates has the Abu Dhabi-Fujairah pipeline, which also terminates at the Indian Ocean. That adds another 1.5 million barrels per day, a completely insufficient capacity. The only real solution, the only one that would truly eliminate dependence on Hormuz, is a navigable canal, deep enough for supertankers, wide enough for two-way traffic, and long enough to completely bypass Iranian territory and the strait. And that means crossing one of the most inhospitable deserts on the planet. This is the first problem. There is not just one option. Engineers and geopolitical analysts have debated for decades what the ideal route would be. The most direct option would begin in the northern Persian Gulf, on the coast of Kuwait or Iraq, cross the Arabian Peninsula from north to south, and terminate in the Gulf of Oman or directly in the Indian Ocean. The distance is staggering. Depending on the exact route, it ranges from 800 to 1,000 kilometers in a straight line through the desert. For comparison, the Suez Canal is 193 kilometers long and the Panama Canal is 82 kilometers. This canal would be 4 to 6 times longer than the Suez Canal, the largest artificial canal in history, by an absurd margin. But distance is not the only obstacle. The terrain is the real problem. The Arabian Peninsula is not flat. It has mountain ranges, sedimentary basins, shifting sand dunes, rocky plateaus, and deep valleys that cut across the route at impossible angles. The difference in elevation between the Persian Gulf and the Indian Ocean can exceed 1,000 meters in some stretches of the route. And unlike the Suez Canal, which was dug through almost completely flat terrain, this project would require moving mountains, literally, water. The second problem, and perhaps the most complicated, is that a canal needs water. not only for the initial filling, but also to maintain the level, compensate for evaporation, and operate the locks. The Persian Gulf and the Indian Ocean are at different levels. The average difference is about 1.5 meters, though it varies with the tides and the seasons. This means the canal cannot simply be a trench cut from one point to another. It requires locks, controlled water chambers that raise or lower ships between different sections of the canal at different elevations. And in a desert where temperatures can exceed 55 degrees Celsius, evaporation is devastating. A canal of this length, under these climatic conditions, would lose tens of millions of cubic meters of water annually to evaporation, water that would have to be constantly replenished in one of the driest places on Earth. The technical solution exists. Desalination plants along the canal's route, combined with a gate system to minimize losses. But each large-capacity desalination plant costs between $500 million and $2 billion, and dozens of them would be needed. The canal's water infrastructure alone would cost more than many complete engineering projects. The dimensions. This is where the scale of the project becomes truly incomprehensible. For a VLCC-class supertanker to navigate fully loaded, the canal requires a minimum depth of 25 meters. The largest vessels, the ULCCs, require 28 meters. We would build for the largest 28 meters of depth, without exception. Width. To ensure the safety of bidirectional supertanker traffic with vessels 60 meters wide, the canal must be at least 250 meters wide in its navigable section. Including the embankments, the total working area exceeds 400 meters in width, 28 meters deep, and 1,000 kilometers long. The volume of material to be excavated is astronomical. To put this in perspective, the Panama Canal required the movement of 150 million cubic meters of earth, one of the greatest engineering projects in history. This canal would require the movement of between 15 and 20 billion cubic meters, 100 times more. If all that material were loaded onto construction trucks, the line of trucks would circle the earth 40 times. The excavation. Never before in human history has anything of this scale been attempted, but engineers have tools that previous generations did not. Cutter suction dredgers are the giants that would handle the job in shallow waters, floating factory ships with a rotating cutting head at the bow that grinds the seabed and suctions the material up like an industrial vacuum cleaner. The largest dredgers in the world can dredge 100,000 cubic meters per day, but in the high elevation sections where the canal must cut through hard rock, dredgers are useless. That is where controlled explosives come in. Teams of explosives engineers drill into the rock following calculated patterns. They set charges of dynamite and ANFO and detonate entire sections of mountainside in coordinated operations. The scale of the detonations required is comparable only to open-pit mining. The largest copper mines in the world, in Chile and Peru, give some sense of what would be needed. But here, no ore is being extracted. The terrain is simply being cleared. Then come the excavators. The largest ones manufactured by Liebherr and Komatsu, 800-ton machines with 40 cubic meter buckets, operating in coordinated fleets like armies of steel, carving their way through the desert. The excavated material does not disappear. It has to go somewhere. In coastal areas, some of it could be used to create new land platforms at sea, similar to what was done in Dover with the Channel Tunnel, but on an infinitely larger scale. In inland areas, enormous spoil deposits of gigantic proportions would have to be created, new artificial hills rising in the middle of the desert. The locks are the operational heart of the canal. Without them, nothing works. At least 6 lock complexes would be needed along the route, located at the points where the elevation difference between sections is greatest. Each lock complex is not just a structure, it is a city of concrete. The expanded Panama Canal locks, currently the largest in the world, have chambers 427 meters long, 55 meters wide, and 18.3 meters deep. Even so, the largest supertankers cannot pass through them. The locks on this canal would have to be larger, at least 500 meters long, 70 meters wide, and 30 meters deep. The gates on each lock would weigh thousands of tons. They would be the largest movable structures ever built, and 6 complexes of this type would have to be erected in the middle of the desert, hundreds of kilometers from any port. The locks alone would represent decades of work for the world's largest construction companies. And then there is the concrete. All of this requires concrete in unimaginable quantities. The project includes the lining of the canal, the locks, the dikes, the control structures, and the bridges that would cross it to connect communities separated by it. Estimates suggest the project would require more than 500 million tons of concrete. To produce that quantity, dozens of cement factories would have to be built specifically for the project. Limestone, clay, and sand would have to be extracted in quantities that only industrial-scale mining can provide. And in the Arabian desert, where the heat causes concrete to harden far too quickly, the same techniques used on the Burj Khalifa would have to be employed. Ice in the mix, nighttime pouring, admixtures, superplasticizers, but not for a single building, rather for thousands of kilometers of structures. Human logistics. A project of this magnitude cannot be completed with locally available labor. Estimates suggest that at peak construction, the canal would directly employ between 300,000 and 500,000 workers, with a similar number engaged in indirect activities such as materials production, transportation, food services, medical services, and security. 1 million people living and working in the desert. Temporary cities, water and sanitation infrastructure, field hospitals, internal transportation systems, and electrical grids would all have to be built, all in an environment where summer temperatures exceed 50 degrees Celsius and sandstorms can last for days. The workers on the Burj Khalifa faced extreme conditions, with 12,000 people crowded onto a site of just a few hectares. Here, 500,000 people would be spread across 1,000 kilometers. The logistics alone would constitute one of the greatest challenges in the history of project management. And then there is the question of time. How long would it take to build? The Suez Canal took 10 years to build. The Panama Canal took 34 years from the first failed attempt to its definitive inauguration. With modern machinery, current techniques, uninterrupted funding, and firm political will, the most optimistic engineers speak of 25 to 30 years. The more realistic ones say 40. And that assumes no wars, no economic crises, that the sand does not swallow the machinery, that the heat does not bring construction to a halt during the summer, that the geopolitical conflicts of the region do not disrupt the supply of materials, and that the underground aquifers crossed by the route do not generate unexpected flooding. Every single one of those risks is absolutely real in that region. The cost estimate of $200 billion is the most frequently cited figure, and it is almost certainly an underestimate. The expansion of the Panama Canal cost $5.25 billion. The Channel Tunnel cost twice its initial budget. California's high-speed rail project, which began with a budget of $33 billion, has already surpassed $100 billion in unfinished costs. Mega infrastructure projects systematically exceed their budgets. The historical average cost overrun for projects of this type ranges between 200 and 300%. If the Hormuz Canal follows that trend, the real cost could exceed $500 billion, $500 billion. To put that in context, Saudi Arabia, the wealthiest country in the region, has an annual GDP of approximately $1.1 trillion. The project would consume nearly half the kingdom's annual wealth, and it would still be worth every cent. The return. What justifies such an investment? Every barrel of oil passing through the Strait of Hormuz is currently worth between $60 and $70, multiplied by 20 million barrels per day. The value of the daily flow exceeds $1.5 billion, adding up to more than $550 billion per year in oil and liquefied gas. A single year of closure of the Hormuz Canal would cost the global economy more than the construction cost of the canal itself. Furthermore, the canal would not only prevent closures, it would also reduce maritime insurance premiums, which spike during periods of crisis, lower the operating costs of supertanker fleets, create new trade routes along its length, and generate cities, ports, and industrial zones in territories that are currently completely uninhabited and inhospitable. The canal would not merely be a waterway. It would be the development axis of an entire region, presenting obstacles that no engineer can overcome. Engineering has answers for almost all the technical problems of this project, but there are obstacles that cannot be solved with concrete and steel. The first is political. The canal would cross the sovereign territories of several countries: Saudi Arabia, Oman, possibly Yemen, possibly the United Arab Emirates, each with its own interests, its own conditions, its own border disputes. Reaching agreement among all of them on a 30-year project may be harder than building the canal itself. The second is environmental. Connecting the Persian Gulf to the Indian Ocean through an artificial canal would create a corridor through which the marine ecosystems of both basins could intermingle. Invasive species would move in both directions. Temperature and salinity patterns would be altered, effects impossible to predict in full. The Suez Canal has already created this problem. Hundreds of marine species from the Red Sea have colonized the Mediterranean through the canal. This phenomenon is known as Lessepian migration. A canal between the Persian Gulf and the Indian Ocean could create an equivalent or even greater problem. The third issue is seismic. The Arabian Peninsula is not an area of high seismic activity, but it is not stable either. Active faults exist. There is residual volcanic activity in some areas. An earthquake of moderate magnitude along the route could damage entire sections of the canal lining. Will it ever be built? Today, the project does not officially exist. No consortium of countries has approved it. No funding has been secured. No detailed engineering design has been produced. But feasibility studies do exist. Preliminary plans have been drawn up. Diplomatic conversations have taken place in discreet meetings that never made headlines. And every time Iran threatens to close the Strait of Hormuz, the project returns to the desks of ministers and the boardrooms of the major oil companies. Political will fluctuates. Urgency rises and falls with the geopolitical climate of the region. But the need is constant. The vulnerability of Hormuz does not disappear, is not negotiable, and cannot be permanently eliminated. And as long as that vulnerability exists, the most ambitious canal in human history will remain not merely an engineer's dream, but a strategic necessity that the world, sooner or later, will be forced to confront. On the day they begin to move the first grain of sand, nothing will ever be the same again.